let's go to the fourth one. The title is Influence of Valve Spool Shoulder Wall Angle on the Steady State Hydraulic Force. It is by Ziwei Wang. Ziwei Wang is a student of Hunan University of Science and Technology.
Hello everyone, my name is Wang Ziwei. I'm from Hunan University of Science and Technology. I'm very glad to have this opportunity to attend the conference, the International Conference on Advanced Vehicle Powertrains. Today I would like to share with you some of my research progresses on the influence of valve shoulder wall angle on steady-state hydraulic, which is also the title of my paper. My presentation will include these 4 parts: background, approach, simulation, and the conclusion. First, I would like to give you a bit of background. The electro-hydraulic control model is a key component of the transmission system, and with the increase of the percentage of electric power in the vehicle, the transmission system has to increase response speed, which leads to increase in instantaneous flow required by the actuator. Furthermore, large flow will affect the control accuracy as a change of dynamic response characteristics between valve spur and valve housing. Therefore, it's necessary to study the dynamic response characteristics of valve coil. The valve spur or pressure regulating valve will be affected by various forces, which can be divided into axial force and radical force, according to the direction. The radical force mostly offsets because of the whole fluid area is filled by the oil. If the structure design is reasonable, the radical force and the friction between the valve spur and the valve housing can be ignored. Hydraulic force can be divided into transient hydraulic force and the steady-state hydraulic force. Steady-state force is the result of the change in momentum caused by velocity and direction difference before after valve. Transient force refers to the movement of the valve spur due to the change of its momentum when the oil flows. Compared with steady-state force, transient force has less influence. So this paper mainly studies the axial steady-state hydraulic force. Now let me move on to the approach. There are many methods to solve the force, which can be roughly divided into 2 categories: theoretical analysis method and the numerical solution method. As far as theoretical method is concerned, when the oil flows in the valve, if the expression of velocity disruption near the wall of the valve body can be obtained, and then the expression of pressure distribution will be obtained by Bernoulli equation. The force of oil on the wall can be obtained theoretically, and it can be subtracted by this force, which is the steady-state hydrodynamic force, and its formula can be expressed as follows. For the theoretical calculation method, the momentum method is usually used to deduce the steady-state hydraulic force by calculating the change of oil momentum difference between the inlet and outlet. For the numerical solution method, we usually rely on computer simulation software, such as Fluent. Now we are going to take a look at the next section, the simulation. The simulation is carried out in the following 4 steps: geometric model import, fluid domain extraction and meshing, boundary conditions, and calculation. The simulation object used in this paper is the main pressure regulating valve or hydraulic system of an auto transmission. The slide valve is located in the main oil path of the system, and the flow between the inlet and the outlet is large. So the steady-state hydraulic force generated by it is correspondingly large. In actual working condition, the valve spool has the longest working time when the opening is 2 millimeters. Therefore, this paper mainly studies the opening of this valve port. In the meshing phase, to balance the relationship between calculation accuracy and the calculation efficiency, the method of block interruption is adopted. The mesh at the shoulder and jet orifice is locally interrupted. The number of finally generated mesh units is about 1,420,000, and the number of nodes is 430,000. The average gradient of the mesh is 0.27. The average orthogonal quality is 0.73, and the overall mesh quality is good. In order to make the simulation results fit the actual situation and reduce the computer calculation burden, some models are simplified and some boundary conditions and assumptions are set. For example, fluid is Newtonian fluid and incompressible. The slide wall is an ideal slide wall without the consideration of the radical phase gain between the wall body and the wall spool. The remaining boundary is contact with oil is a static non-slip wall. According to relevant literature, this paper selects model as a calculation model of the flow field simulation of the slide wall. By selecting the calculation interaction step and the residual wall, the final result is obtained by calculation. The pressure diaphragm and the velocity vector diagram of the profile derived from fluid are shown in Figure 2 and Figure 3. It can be seen from the pressure graph that the oil pressure in the left chamber basically maintains an inlet pressure of 5 millipascals, and the pressure changes obviously at the wall port, and the pressure value shows a downward trend. It can be seen from the velocity vector diagram that the oil directly impacts the right side after flowing through the wall port, which causes the valve spool to be forced to the right. The oil flow rate is high and obviously jet phenomenon appears. At the same time, it also appears that the oil flows through the valve port and enters the right chamber, generating vortex. And there is a small amount of vortex at the intersection of valve spool and valve body. It can be seen from the calculation result that the total steady-state hydraulic force on the valve spool is 53.17 N, and the direction is left, which tends to open the valve. The incidence angle varies from 30 degrees to 75 degrees, and the exit angle varies from 85 degrees to 45 degrees. Comparing results of theoretical calculation and simulation calculation with the experimental data, it can be seen that when the valve opening is 2 millimeters, the axial hydraulic force on the valve spool is larger, and this force tends to increase the valve opening, which has a great influence on the stability control. In order to reduce the axial steady-state hydraulic force on the spool and minimize the influence of this force, the structure is improved from the angle of jet flow. Keep exit angle is unchanged. Change the value of incidence angle from 30 degrees to 75. Every new model is established with 5 degrees intervals, with 10 growths in total. And keep incidence angle is unchanged. Change the value of exit angle from 85 degrees to 45 degrees. Every new model is established with 5 degrees with 9 groups in total. Assemble 19 groups of wall spots with the original wall body and keep the wall pod opening at 2 mm. Repeat the simulation steps shown above and finally get the axial static hydraulic force of each group. The results are shown in Figure 4 and Figure 5. Through the calculation results and the analysis of the previous 3 conclusions are finally obtained. When the wall pod walks, the fluid has a great impact on the wall surface, and the flow velocity is rapid. A combined action of the 2 factors lead to the axial static hydraulic force on the wall coil is large. When the wall opening is 2 mm, if exit angle is kept at 85 degrees and change the incident angle, the hydraulic force will change and get smallest value when the incident angle is 70 degrees. If incident angle is kept at 70 degrees and change the exit angle, we found that static hydraulic force doesn't always tend to make the wall pod close. And when the exit angle is 72 degrees, the hydraulic force is 0. That's all for my presentation. Thank you for your attention.
Okay, now it's time for question and answer. If any question?
Okay, I have a question.
Thank you.
Again, Nong Zhang from Hebei University of Technology. Yeah, your simulation results are interesting. I believe probably true. Have you done any experiment to validate your simulation result?
No, just do the opening at 2 mm because the wall spot has the longest working time on the position.
Fluid probably have some properties like viscosity and temperature and these things.
No, I didn't do that.
So you think the temperature and the viscosity coefficient will not make any difference to your result?
Yes, I didn't consider the temperature and so on.
Mm-hmm. Okay, thank you.
Thank you.
Okay, I noticed that when you do such simulation, the valve opening is always 2 mm, yes? Why?
Yeah. Because in actual working condition, the wall spot has the longest working time when the opening is 2 mm. So the paper mainly studies the opening of this wall spot.
Okay, other questions? Okay, thank you.